Hello students, welcome to this lesson on how to create theoretical models for your projectile motion launchers. We're going to do this basically using an Excel spreadsheet. This is the spreadsheet here, and you'll find this one. So this is just an example of one that's been done before. So we're going to have to modify it, but you'll find it sitting inside the 11 physics folder on the student share drive. So the name of the file is Projectile Motion Drag Numerical. Okay, so that's what we're going to be working with mainly here today. The other thing I'll quickly show you is a flow chart of the overall analysis and evaluation process that we're going to be doing for this EEI. Okay, so just to start with, you'll hopefully by now you'll have all your data. You will have put it into Excel, and maybe even at this point you've averaged out your results. So you might end up with a summary table like this. So if we have a look at this table here, this is mocked up. So this is in no way representing anyone's data in particular. It's just one that I've made up, and it just so happens that the values work out pretty close to what we expect them to work out theoretically. So in this example, we're looking at launch angles ranging from 25 up to 50 and moving up in increments of 5 degrees. Okay, and if we have a look at just a quick look at this data here, you can see that that the range is increasing and then sort of peaking at around 35 degrees and then obviously diminishing thereafter. So it's a bit of a, just looking at this very quickly, it's a bit of a tussle between 35 and 40. Maybe there's somewhere in between there. The optimum angle could be 36, 37. We don't know, but just looking at this and making a quick conclusion, we'd say that certainly 35 degrees is the optimal angle. When I say optimal, I mean optimal in the sense of being able to project that object, that tennis ball, the furthest distance that we can get it. Okay, and just bear in mind that this data here is obviously the experimental data that you've taken from the field. The data, the launches that you performed, the balls underwent obviously acceleration and deceleration. The main force that we're needing to consider here is air resistance. If we take air resistance away and basically assume there's no drag, then we would expect the optimal angle to be about 45 degrees, and that the theoretical models show that. So, but clearly we're working with air resistance, so we find that the optimal angle is actually a little bit less. So if we can launch our objects at a lower angle, we expect them to go a little bit further because we reduce the effects of air resistance. Okay, so hopefully at this point, when you have the summary of your experimental data, you can look at it and say, well yeah, the optimal angle does look less than 45. It doesn't necessarily have to look like the data over here, but if it does, good. If not, that's still good. The main purpose of the investigation here is that we can look at the data that we've obtained, and we can sort of evaluate it and make some conclusions about, well, why is this data like it is? What happened? What are some of the factors that affected the flight? So that's really what we're trying to unearth in this investigation. Okay, let's move through the flow chart then. So we have the experimental data here. Now we should also have some extra data, which is the calculation of the launch velocities. That's using the tracker program. So the previous video that I produced takes you through the steps for using the tracker program. So you import your video, the launch video into Tracker, and you go through the steps, and you should figure out some sort of velocity, and it might be around these values. I don't know. I've looked at a few, and I think some of them were around about 35, 40 meters per second. So again, I've just mocked these up. So given that you have 3 videos that you can analyze, and it doesn't matter what angle they're launched at, we'll just assume that every launch was identical in the sense that there was the same amount of pressure in the PVC pipe gun, and the release of the valve was consistent throughout every launch. So, it's a pretty big assumption to make, but we'll make it anyway, and we'll expect that the launch velocities, they're going to vary from launch to launch, but maybe by not too much. Okay, but of course later on we can talk about, well, actually maybe that's a wrong assumption to make and explain why. Okay, but anyway, we're making that assumption, and so with the 3 videos that I've pretended to analyze using Tracker, these are the 3 velocities I've come up with. So the initial velocity of the ball as it leaves the gun, or it leaves the cannon. So I average them, and I end up with 41 meters per second. So ultimately, 41 meters per second is going to be the go-to launch velocity that I consider every time when I'm constructing the theoretical models, which I will eventually compare against this experimental data here. Okay, so all right. So step 1, summarize your data, average it out, present it in a table like this. Step 2, work out this extra data, the launch velocity. Step 3, work out the theoretical data. Okay, now to do this, we need to go back to this Excel spreadsheet here, and we need to basically input our launch velocity and our angles. Okay, so I'm not going to do 6 right here and now. I'll probably do a couple, but enough to get you going, so you can have a feel for how to do it. But you will have to do as many trials as you have done experimentally. So, considering that this mock-up here, I've got 6 trials, 6 different angles. In my theoretical analysis, I will need to do the same six angles. Okay, so if we have a quick look at the steps here. So we're basically simulating in the Excel spreadsheet to gather some theoretical data for range and time of flight. We'll need the inputs will be the elevation, angle of elevation, and the launch velocity, which we have here is 41. Okay, so really the only numbers I need to remember for inputting are 41 for the velocity, and then 25, 30, 35, etc. up to 50 for the angles. Okay, so we input them into the spreadsheet, we repeat it for each angle, and then from the spreadsheet we can read off the range and time of flight data. Also from the spreadsheet we'll be able to get some really nice graphs which we can use in our final report as a way of just giving a visual picture of what these theoretical trajectories should look like. Okay, there is a step that follows on from this, and it's really more the next phase in the process, and that is evaluating the data. I won't go through that now because really the focus of this lesson right here and now is to look at how to use a spreadsheet. Okay, but you'll have access to this handout, and here it's just a list of ways of how you can basically critique your data. Okay, so without further ado, let's now open the spreadsheet. Now you'll see that the version that's available to you, it won't necessarily have these cells highlighted yellow. It may or may not, I can't remember. But that's essentially the 2 sections where you're inputting. What you will notice is the initial velocity will be 60 in every single case. So if we just go through the tabs here, you can see that yes, 60 is the launch velocity. Now, remember back here I said the launch velocity was 41. So I need to go through and change all of those. Otherwise, everything else doesn't change because it's already, you can see I've already set up these tabs to look at angles, ranging from 25 up to 50 at 5-degree increments. So most of the work is kind of already done here. The only thing I really need to do, there's a few little tweaks we'll look at, but really all I need to do is input my velocity. So you'll have an average launch velocity that you've come up with. You just need to put it in here. Okay, so here we go. So 25 degrees launch velocity, that will have an initial velocity of 41. 30 degrees, we'll make that 41 as well. 35, 41, so really quite simple, really straightforward what I'm doing here. And I guess what I should have done before I started was to show you the graph, but that's okay. We'll see. We'll look at it after I've made these changes. So I've gone through. I've done that. So every single theoretical model here. So each sheet here is a theoretical model for how the ball travelled in terms of position, velocity, and acceleration. The formulas behind this, I'm not going to explain them now, but maybe a subsequent lesson we can look at those. But just accept that it all works for now. And let's have a look at the graph. Okay, so over here we have theoretical trajectory plots, okay, or plots of the theoretical trajectory. So you can see here that they're all launching from 0, 0. So y is height, x is horizontal distance. You can see some of them go below the ground, so we can just ignore that for the moment, and we're more interested in, or we're really interested just in where it intersects the x-axis here. So, and that tells us the distance of where it hits the ground. Now, just having a quick look at this here, you can see that it's a bit of a close call between these two here, the purple and the green. So the 35, the 40 degree. So to really get an accurate number on the distance that's been travelled here, we have to go back to the spreadsheets. But even so, this gives you a really nice picture of what should happen, or what does happen actually. But theoretically, this is what should happen. And I guess another way to really point out the difference between incorporating air resistance into your model versus not is to have a look at this other plot. Where is it? This one here. Okay, so if we have a look at this here, we can see that something's not right. So what I need to do, okay, over here we have no drag. So this one here, and what I'll do is I'll highlight the inputs here as well, just to point out that these are the only two things we really need to tweak. While I'm here, actually, I might as well say what's with all of these. I'll say that we have all the parameters set up here, so the mass of the tennis ball, the diameter. These should all be pretty accurate, okay? Because they're all based on standard tennis ball. The cross-sectional area, the coefficient. Okay, so here it's 0. The drag coefficient is 0 because we're saying there's no drag, okay? But if we go to one of these other ones here, you can see the coefficient of drag is 0.6. Density of air 1.2, etc. Okay, back to the no drag one. The initial velocity here should be 41, just like the other ones. The angle is, well, I think it's 20. Let's just see what happens. So we go back to this plot. Okay, good. So what this plot is doing, it's got two. It's got the trajectory of the tennis ball if we assume there's no drag, and it's got one where there is drag. Now this is not complete, this one here. I can actually go in and change the numbers a bit here. Let me just do that now. I'll just push these numbers forward a bit, maybe, I don't know, well, let's try 400, see what that does. And I'll do the same thing down here, push that forward to 400. And let's see if that makes a difference. Okay, it was the wrong one. How about that, eh? Or was it? No, actually, so it's the red one is no drag. So that's the one I need to really push forward. So no drag is that one. Yeah, I think I did the wrong one. Never mind. So we'll make that 400. And we'll push that forward to 400 as well. And see what that does. Okay, better. Obviously, it'd be nice if we could just clip them off at this point here. And really all you're doing, and what I just did there, just to explain what I did there, is we're plotting X and Y data. So X is horizontal data, Y is vertical data, and positional data. And if we look at this spreadsheet, how many cells are we going down to? We go down to about, well, it looks like about 750. So we don't need to incorporate all of that data there, because at some point, if we look at the Y column in particular, at some point, you can see if we follow it down, you can see the numbers increase. So that's reflecting, that the ball is increasing its height. So it's on the up. At some point it will peak. So you can see we're getting around 9, 10. Okay, now we're back to 9. So it's peaked, it's on the way down. Eventually we get down to somewhere close to 0, and we'll stop there when we get close to 0. So about there, right? So you can see, I don't know, probably this one here or this one here. Maybe this one here. So I'll just highlight that there just to really indicate what we're looking at here. So this is suggesting that the ball's hitting the ground after about 2.86 seconds, because this is the time column, and after it's travelled 110.188 meters horizontally. So effectively, that's my range and that's my time of flight, those two numbers there. And this one here is we're looking for the number here that's as close to zero as possible, because that's suggesting where it's hitting the ground or passing through the ground in this sense, I guess. Mind you, we don't need this data because this is for the no drag situation. We need to do this process for all the other ones, okay? But the other thing to note is that this happens at about cell 290. So if I scroll back up, and just to put it back to that position there, and then I go to my plot, what I can then do is I can select my data and go to the no drag one, and I think I said that was about 290, didn't I? So let's just make it 300. 300. And so that means we just need to plot the columns, so the X column, the Y column, just down to cell 300, okay? And there it is, okay? And we can do the same thing for this one. Now, look, without going into the actual columns and looking at what cell we should go up to, what I might do is, I'll just guess. So this one is for with drag. So with drag, so we'll go in here again. So I'm going to guess, and let's just go with 300, see what that does for us. 300. Okay, let's see what this does. Okay, that's better. All right, so this is a good picture because it says if we don't have air resistance, then the ball's going to travel just over 110 meters. But if we do have air resistance, it's not going to travel that far. Now I have a concern that this is not correct. This if we check, let's just go back and check. So the width drag is when it's at a 25-degree launch angle. So that is coming off this one here. So that means the angle of elevation is 25, which means in the no drag spreadsheet, I need to make my angle 25. So that's one last, okay, let's get that right. That's fixed. Okay, let's go back to the plot now. That's better. Oh, and look what happened. So now we need to, so you can see this is a bit of, backwards and forwards, but we're getting there. Okay. Select data, no drag, and well, I think I'll just push it back to 400. How about that, eh? 400. Done. Okay, so what we can see now is that when we don't have drag, the ball, we expect theoretically will travel 130 meters. That's a long way. Wow. With drag though, less than 60, just under 60, maybe 55. So you can see the effect of drag is significant. It really is significant. And that's why we can't ignore it. Okay. So that's at a launch angle of 25 degrees with a launch velocity of not 60. We changed it to 41. There we go. Okay. Now that's a worthwhile graph to include in your report because it just justifies why we need to incorporate drag into our calculations. Okay. If we don't, then obviously there's no way of really analysing our experimental data. So there you go. All right, good. Now back to this one. You can see these are all with drag. So you can imagine if we did all of these models here, computed them all, calculated them based on no air resistance, you could imagine that the trajectories would be way out beyond 100, 150, 200 meters even for some of these things, right? But you can see that drag really does push the ball back, horizontally, and it kind of skews the shape of the trajectory. So, coming back to this one, the red line here is a pure parabola with no air resistance. It's basically a quadratic function that models that. But this one here, you can see the quadratic function's being kind of sheared by the effect of air resistance. Okay, so this sort of force, this air resistance force, it's pushing in that direction. Okay, so I guess the last thing I'll mention here, I'll show you what to do here, is to how to get the, and I've kind of shown you anyway, but I'll go through it. How do we get the range, so the horizontal distance and the time for each of these models? Okay, so let's do that now. So 25 degrees with drag. You can see that the Y column here is highlighted. That's to really highlight the idea that we need to chase this column down until we find it gets to 0. So it starts at 0, it increases as the ball's increasing, it peaks at some point, around about 9 meters, I guess, and comes back down, and it hits 0 somewhere, or close to, the closest we can get to 0 is probably this value here. So you can just go in and highlight that, I guess. And so what that's saying here is that the launch at 25 degrees at 41 meters per second theoretically will travel a horizontal distance or a range of 55.37 meters. It will take 2.68 seconds to do it. So that is theoretical data right there. So what we can then do is just remember these numbers: 2.68, 55.4. We'll just round it out. 2.68, 55.4. So 55.4 and 2.68. So there we go. And what does this all mean? Well, what does it mean? It means that we now have theoretical data for the 25 degree angle of elevation launch that we can now compare to our experimental data here. So let's do a quick comparison. Now, the time of flight is pretty close. The range, okay, well, we've sort of overestimated theoretically what our range is going to be, or we could say our, excuse me, and we could say our experimental data, undershoots what it should be theoretically. So interesting. Now, that's in no way is that enough to really gain a true picture of what's happening. We need to go through and do it for each one of those. So we need to come back in here and go to the 30 degree launch. Same thing again, chase the Y column down until we find a 0. So let's have a look here. What have we got? I'd say that's probably the closest one there. So we're saying at 30 degree launch, time flight is about 3.09. Horizontal range is 58.1. So 3.09 or 58.1, 3.09. 58.9. Okay, bad memory. 58.1. 58.1, and that was 3.09, I believe. Okay, and comparing that up here, okay, 30 degrees, experimentally went 50 meters, theoretically 58. Okay, so we're undershooting, our experimental data undershoots what the theoretical data suggests, but the time of flight is close. Last thing I'll kind of quickly mention here, obviously we need to go through and do it for the rest of these. Once you have all that, once you have this theoretical data, you can then compare it to the experimental data, and that's essentially the evaluation stage here. Just remember though that the theoretical data is an approximation, and there are assumptions that have been made in here as well in calculating this. Many assumptions lying behind this model here, but at least we have some guide, some reference that we can compare against. Okay, and probably the more reliable data. Now, I would expect the range to be more reliable than the time of flight, but hey, they both might be quite unreliable. But the reason I would suggest the time of flight data is unreliable is because you tend to gain quite a bit of human error in your time of flight data, and that's because you have human error every time you hit the stopwatch, and you do that twice in the timing. These time intervals are quite small, So proportionally, the human error is quite significant. Okay, so you may not prefer to use your time of flight data in your evaluation. It's probably worth a mention, but it's more the point that we should look at the range. And in fact, if your hypothesis is really about angle versus range, we hypothesize that the optimal angle for gaining maximum range will be something less than 45 degrees. Then your hypothesis is really just about the range in terms of the angle of elevation, or the range as a function of the angle of elevation. So that doesn't incorporate time of flight. Time of flight is good to have. It's kind of a backup set of numbers that you can still use and still compare. And in fact, when you come down and do your evaluation, I've suggested in here you should do some plots where you compare the experimental range to the theoretical range, but also do the same for time of flight. Okay, I might stop here now. So just a quick summary. This here is a good guide for you, just to take you through the analysis evaluation stage of the investigation and the reporting part. This is really a time consuming part. Once you get through this, then it's really just doing your write up and incorporating all the issues that may have arisen and affected your data. This is the magic spreadsheet that we're using, and it's probably at some point we'll probably need to sort of unpack this a bit more and explain how this is constructed and why it works and why it's a good model to use. Okay, but I think that'll do for now. Thanks for listening.